So, welcome everybody to my talk about the paper Small Hazard-Free Transducers. This is joint work of Christoph Lenzen, Moti Medina and myself. I am Johannes Bund. What we are studying is the complexity of circuits in ternary logic. The variant of ternary logic we are looking at was introduced by Stephen Cole-Cleany. What we do is we take the set of Boolean values and add a third logical value. The value is called u, which is an abbreviation for uncertain. U can be regarded as the superposition of the Boolean values, which means that u may evaluate eventually to 0 or 1 or at some point, but the evaluation of u is unpredictable. So for worst case analysis, we say that uncertainty propagates. A u will always stay a u. As an example for what is the difference between binary and ternary logic, we can look at the law of non-contradiction. In binary logic, x and not x will always evaluate to 0 for any value that we plug into variable x. In ternary logic, the law is not true anymore. We can plug in value u. Then u and not u will evaluate to u instead of 0. So this is why the law does not hold anymore. What is our motivation to look into ternary logic? Well, eventually the inputs to a circuit will be analog signals. Binary values are just an abstraction of these analog signals. With a third logical value, we cover analog behavior that cannot be clearly interpreted as 0 or 1. For circuits, we want to compute the most precise output in face of uncertain inputs. So we call circuits that compute the most precise output in face of uncertainty hazard-free circuits. We can also define formally what is a hazard-free circuit. But to do so, I need to introduce two tools that map from the ternary world to binary and back. There is the resolution that produces a set of binary words from a ternary input, and the superposition that maps a set of binary inputs to a ternary word. First, the resolution is formally given by the set of all binary words that match input x in every position where x is not uncertain. Think of it as replacing each u in x by 0 and 1. Second, the superposition, which is denoted by the star operator, compares two binary words bit by bit and replaces every position that does not match by a u. The formal definition is given for two words, but because of associativity and commutativity, this can be applied to any set, regardless of the order of application. Take this example. For example, the resolution of 0 UU is the set 000, 001, 010, and 011. So we replace every occurrence of a u by 0 and 1. On the other hand, the superposition of words 010 and 001 is the word 0UU. So each position that does not match is replaced by u. With these two tools at hand, we can define the hazard-free extension of a function. Assume we are given a function f that is defined in binary words, then its hazard-free extension is denoted by f subscript u. And it is defined by looking at each possible resolution of the input, evaluating each resolution, and taking the star of all evaluations. And that's basically the definition of a hazard-free circuit as well. A circuit C implementing function f has a hazard if there is an input x that may have some uncertainty, such that the output of C on x does not match the hazard-free extension of f applied to x. So, and finally, a circuit is hazard-free if it has no hazards. Please note that it is equivalent to say that circuit C implements f subscript u, or circuit C implements f and circuit C is hazard-free. Before we come to our result, let me show you what is known on hazard-free circuits. First, by Huffman, we know that every Boolean function has a hazard-free implementation. This means for any function f, there is a circuit C that implements f subscript u. Next, by Ickenmeyer and his co-authors, we know that there is an exponential gap between Boolean circuit size and hazard-free circuit size. To be more specific, there exists a family of functions such that for any function f from this family, the following holds. The smallest Boolean circuit implementing f is exponentially smaller than the smallest circuit implementing f subscript u. So these two statements raise the question whether there are functions that have an efficient hazard-free implementation. Finally, this brings us to the results that we want to present today. So all transducers have an efficient hazard-free implementation. Transducers are defined the usual way. There's a Mealy machine with state space S, starting state S0, input alphabet sigma, output alphabet lambda, and transition and output functions T and O. For an input sequence of fixed length n, the Mealy machine induces a transcription function tau. So, the main result of the presented paper is that there is a hazard-free circuit implementing transcription function tau, and this circuit has size linear in n and depth logarithmic in n. To be more specific, the size is given by 2 to the size of the state space plus the size of the input encoding times n, and the depth of the circuit is given by the size of the state space times log n plus the size of the input encoding. Which means for constant size state space and constant size input encoding, this is asymptotically optimal, though constants might get large and impractical for large Mealy machines. What is under the hood of this construction is the parallel prefix computation of Lardner and Fischer. It is known for producing fast circuits for addition, and it is still used in adders today. But there is more to it. Lardner and Fischer not only describe how to do addition, they actually present a framework that can turn any transducer into an efficient circuit. In general, the problem is that states traversed by the Mealy machine can only be computed sequentially. The transition function t can only compute state I from the previous state as I-1 and input sigma I. Following this scheme would give us a circuit of a linear depth. This would be suboptimal. In their solution, Lardner and Fischer recognized that composition of functions is associative. Instead of applying the transition function one by one on each new state, the transition functions are composed together to function pi I. Pi I then is applied to the starting state S0. As function composition is associative, all pi I can be computed by a circuit with logarithmic depth. Unfortunately, the scheme does not directly apply to hazard-free circuits. And the problem here is that encoding matters a lot in the ternary world. For general construction, Lardner and Fischer hint at encoding the transition function by a state transition matrix. In face of uncertainty, the state transition matrix loses information that cannot be recovered later. For example, look at the depicted state machine. If we are in state 0 and our input is uncertain, so it's 0 or 1, then we take either transition 0 or we take a transition 1. We cannot be sure whether we end up in state 0 or state 1. Unfortunately, the standard state transition matrix loses track of the fact that we are in either state 0 or state 1. In the example, we can see that the state machine certainly moves to state 0 if we receive a clear 0 input afterwards. But as the encoding loses track, we cannot retain this information. Our solution is to use a matrix that encodes not only the transition from one state to the next, but also the transitions for every possible subset of the state space. This may seem redundant at first, but it is necessary to keep track of the information that may be lost due to uncertainty. Getting back to the example, if we get an uncertain input, the encoding will become uncertain about state 0 and state 1, but we remain a certain one for the union of state 0 and 1. And we can gain certainty about the state for subsequent input 0. So we don't lose the certainty. Before I come to an end, I want to present a possible application of this framework. This is ongoing research, and what we are aiming at is to apply this framework to addition. A hazard-free addition circuit can be useful in the implementation of clocking schemes, for example. But here again, a major problem is the encoding. Take, for example, the standard binary encoding and look at the encoding of 7, which would be 0, 1, 1, 1. And say we want to add a single bit that happens to be uncertain. Then the hazard-free extension tells us that the most precise output we can compute is the superposition of all possible resolutions. Hence we compute 7 plus 0, which will be 7, so encoded as 0, 1, 1, 1. And we compute 7 plus 1, which will be 8, so this is encoded as 1, 0, 0, 0. The superposition of both results is the word U, 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 U. This output does not contain any certainty at all, and even though we know the output should be 7 or 8. Hence, there is no chance in using the standard binary encoding. In our solution, we assume that the uncertainty is bounded. This is a fair assumption for the clocking applications we are aiming at. Please note that this assumption does not help in the binary world at all. The previous example already shows that the smallest amount of uncertainty leads to fully uncertain output. So what we do is we define a new encoding that is a combination of unary encoding and gray code encoding. Unary encoding alone would already suffice to maintain the amount of uncertainty in the inputs, but it has too much redundancy and is very large. So please recall that the size of the input encoding appears as an exponent in the size of the circuit for our construction. So we are looking for more efficient encodings. But encodings still need to have enough redundancy to cover the uncertainty of the inputs. For a newly defined encoding, addition schemes are unknown, so we have to design according transducers. Then finally, we can apply the presented work to obtain an efficient circuit that is hazard-free. So finally, thank you for your attention.